All right, everyone. Welcome to session D2 of ICALP, where we will be able to discuss 6 wonderful papers. And I was planning to do this in the order as listed, and yeah, then each of the authors will have 2 minutes or roughly 2 minutes to briefly introduce their work. And then after that, we can have a nice discussion. So the first speaker on the list is Michal Wojcicki. Michal, maybe you can, if you have some slides to present, maybe you can share your screen and tell us about your paper, if you're there. You're also still muted.
What about now?
Yes, I can hear you.
Okay. Okay. So as a quick recap of my work, it was about parameterized hardness of approximation, and the problem in question that I focused on was Steiner Orientation, where you have k source sinks pairs, a graph with some directed and undirected edges, and the task was to orient the undirected edges to maximize the number of sourcing pairs that are reachable. I don't think it's meaningful to open my slides right now. So the main idea is to use gap amplification technique, similarly as in the PCP theorem, whereby a series of self reductions. We begin with the original problem, which is W1 hard, and in each step we amplify the gap slightly. And in parameterized reduction, where the original problem is W1 hard, and we are interested in showing that there can be no constant factor approximation in FPT time, it is convenient enough that we can make arbitrarily long chain of reductions as long as this length is a function of the parameter, and we obtain a valid reduction. And as a result of that, we obtain a parameterized inapproximability result that doesn't require strong hardness assumption like a gap exponential time hypothesis, but relies only on the assumption that FPT unequals W1.
All right. Thank you very much. Are there any questions about Michal's paper?
I can also see no questions at Slack.
Yeah, so maybe I can ask a question. So, so this seems to be like pretty powerful compared to reductions from, say, gap ETH. Is this something that we should want to apply to other problems, or are there particular bottlenecks towards doing this?
Yeah, like surely, like we would like to apply this idea. For example, it would be very nice if we could have a similar reduction for k-click, because for now we can rule out any parameterized approximation for k-clique with approximation factor being function of k, but we need to assume gap ETH. So this construction of mine right now it is quite limited because it requires the problem to be somehow related with directed reachability and to some terminals. So another problem that fits into like this setting is directed multicut, and I also like present in my paper application to some approximate version of the directed multicut, but the crucial thing on a higher level is to make self-reduction that is linear in size of the instance. So, for example, for k-clique, we can make power of the graph, which amplifies the approximation gap, but also the size of the graph blows up to the size n to k when we make a k of power. So the crucial thing is to make this reduction work in linear size with respect to the instance, and some other potential area where this kind of reduction can be applied are CSP problems. There are some parameterized approaches to solve CSP, for example, to parameterize them with the number of variables set to true. And also the original PCP theorem can be stated in terms of CSP problems. So I think that a different construction, but also like following the same idea might be doable there.
Yeah, that sounds very interesting. If that would be possible, some good questions. Maybe there's another question somebody wants to ask.
I'd like to ask. So the title of your paper, by gap amplification, it sort of refers back, if I'm not mistaken, to the title of Lyndon's paper proving the PCP theorem by gap amplification. And that makes me wonder about the other way to prove the PCP theorem, as in before Lyndon's proof, there was a proof via locally testable error correcting codes. Is it conceivable that also this other route can give a different route of proving parameterized inapproximability, or does that not have any meaning in the context of, say, graph problems like yours?
So like the PCP theorem is more general than has some more far-reaching consequences than just proving a hardness of approximation for CSP. And in order to make this kind of construction fitting like this regime, one might wonder what would be the parameterized equivalence of the PCP theorem. So like one could say that the original PCP theorem states that class NP can be represented by probabilistically checkable proofs, and maybe some other interpretation of class W1 or WT would be expressible in these terms, and from such a statement, some framework for proving parameterized inapproximability would follow. Yeah, maybe, but I don't have like any idea how to formulate like a parameterized counterpart of PCP theorem.
Okay, thanks.
Thank you. Are there any further questions? If not, then yeah, please ask them on the Slack. Thank you very much, Paul. Then let's move to the next paper about Lyndon arrays, where I think Jonas will present.
Indeed, hello.
Hello.
I hope everybody can see my screen.
Yes, I can see the screen and hear you clearly. Please go ahead.
Very nice. Okay, so my name is Jonas, and today I'm happy to answer your questions about joint work with these many people that you can see on my screen. Yeah, and what we looked into is the space-efficient construction of Lyndon arrays in linear time. I will now just quickly restate the problem and our solution. So maybe if you haven't watched the video yet or gotten into a paper, then this might get you motivated to do so. So let's see, we have the main problem that we look at is a string problem around next and previous smaller suffixes. Let me show this with an example. Given a string, we might look at any text position, here the position 10, the yellow suffix, and we might ask the question, which suffix is the first one to the right of this suffix that is lexicographically smaller? So in this case, the next smaller suffix would be a position 17 over here, because everything that begins in between the 10 and the 17, all of these suffixes, they are lexicographically larger than always fall down. And naturally, we may also ask for the opposite direction. So we might just look to the left side. And in that case, we talk about previous smaller suffixes. And for our example suffix now, the previous smaller suffix is at position 4. And again, everything that starts in between would be lexicographically larger. What we were interested in is a data structure for this problem, such that we just compute the data structure once, and then afterwards we can just query any position, and we get both the next and the previous smaller suffix. And sort of as a minimum requirement for it, we want it to be super efficient, so we want only linear construction time, and queries should be able to be answered in constant time. There are two representations for this that are well known. The first one is to just store two arrays. So you would store one array containing all of the next smaller suffixes, one array containing all of the previous smaller suffixes, which then of course takes n log n bits of memory just to store the data structure. And all previously known algorithms used additional n log n bits of construction space while building the arrays. And with our new algorithm, we reduce this to a constant number of additional words. And then there is also a more sophisticated representation that uses only 2n plus a tiny amount of additional bits. And here as well, the previous best construction algorithms used n log n additional bits. And now here we just use order of n additional bits. And here we'll quickly show the data structure and how it works. It's actually quite simple. So it's called the previous smaller suffix tree, quite pragmatically, because we just take every node and we attach it as a child of its previous smaller suffix. So before we have seen the node 10 had the previous smaller suffix 4. So we just attach node 10 to node 4 in this tree. And then of course we can answer previous smaller suffix queries. And actually we can also answer next smaller suffix queries because we just have to count the size of the subtree that is underneath the node 10. And then we find the next smaller suffix like this. And the final data structure is simply a succinct encoding of this tree that is this parenthesis sequence that takes 2n bits. Questions?
Thank you very much. I saw that there was a question on Slack by Moses Kanadi, and I think Moses is here. Do you want to ask your question yourself?
Yeah, sure. So very nice presentation. So I was wondering whether some of your ideas or techniques can be used for the dynamic setting, where say I can say change some symbols in the text.
That is a very good question indeed. So let me go back to this introductory example. So from a theoretical position, it is kind of difficult because you have a lot of dependencies between positions in the text, and they can actually go in both ways. So now if you for example, you want to change this W to an A, then that would change this edge, because then this edge all of a sudden would have to point here. And at the same time, you would also need to change this edge, because this edge all of a sudden would also point further to the left then. And you can have, in general, it can happen that you change a single character and you might have to change up to n edges. So that is a bit of a problem from a theoretical stand, but actually from a practical position, this looks much different because these edges in practice are not very long. So for all of the text that we looked at, which is like DNA, source files, English text, really a lot of practical real-world examples, and these edges are never very long. They're usually like less than 1% is longer than maybe 64 characters apart. So then if you would change something in between, you would not have to update very much in practice. And then the other thing you might be interested in is just to construct the data structure sort of in an online setting. And that might also be theoretically more easily possible, because you would only need to maintain which characters actually, or which text positions depend on the currently last one. And then when you append a new symbol, you only need to change those.
Thanks.
I have a question. Actually, I have two questions. So you use this support data structure in your algorithm, and you say that it takes little of n bits. It looks like it has to mark as much as theta n locations. I'm wondering how that works.
Well, I mean, it is really a pretty naive modification of the rank and select data structure.
Is that right?
Sorry?
Is that right?
Yeah, it is like that. And you only need to, like, sort of, if you actually wanted to get the theoretical bounds that we claim, then you only need to make sure that you actually sort of update the support data structure sort of in a batched fashion, so that you would say maybe the last square root n parentheses that you have written, for those ones, you just keep all changes naively stored, like in an array or on a stack in a very simple representation. And then you would just like sort of update your support data structure every once in a while when your buffer flows over.
Okay, I see. Fair enough. And then there's one other question I had. So you use these common LCP, you use these common strings to skip when you're trying to make the linear time algorithm. And you claim that the LCP values are non-decreasing, but it seems like that's only true up until the last iteration.
Exactly, yes. That is actually something that is like, I omitted this on purpose in the video presentation. So actually in practice, it's a bit more complicated, where actually we do have to make sure that we don't make mistakes by just assuming that the LCP values are increasing. Okay. But also for this, the solution is essentially just that we like only consider not every single element, but let's say only every few elements, and then every once in a while we check if we made a mistake.
Okay.
Thanks very much. Are there any further questions? If not, then you can always ask them on Slack. Thanks very much, Jonas.
Thanks for stopping by, everyone.
All right. Then we'll move to the next paper in this session on query complexity. And I think I saw Lunja in the chat.
Yes, I'm going to present it. Okay, great. Thanks for coming to the session. I'm Lyndon, and this work is about query complexity. So let me start with the setting. So the setting is that we have a Boolean function f, and we have an input x, and we want to compute f of x by querying some bits of x. We can do the queries adaptively, and the goal is to figure out the function value f of x. So the query complexity is the number of queries we need on the worst case input x. So naturally, the query complexity of f is at most n, because if you know all the bits, you can compute this function. In this work, we are interested in the randomized version and randomized query complexity denoted by R of f. So recall that R of f is defined on the worst case input, but sometimes it's often useful and helpful to consider random inputs, or in other words, inputs coming from a distribution D. And the reason we care about random inputs is because of this famous Yau's minimax principle, which says the randomized query complexity of a Boolean function is witnessed by the hardest distribution D. In other words, there exists an input distribution D such that if you want to compute this function on this input distribution, you need R of f queries. Okay, this is very great, but if you look more closely into this hard distribution, there could be some caveat here. For example, if you think of this XOR function and you consider this distribution, which is designed to be hard 99% of the time, but it's easy for the remaining 1% of the time. And of course, this distribution is a valid distribution for Yau's minimax principle, because it's indeed a hard distribution for XOR. In the sense that if you want to compute XOR with the success probability 2/3, you have to solve the hard instance, because the easy instances come too rarely. So indeed, for this distribution, the query complexity is omega n. However, if you have multiple samples from this distribution and you only want to solve one of the samples, the distribution suddenly becomes very easy to solve, because you can just search for the easy instance, which happens with a constant probability. So you only need a constant number of queries to figure out which instance is easy and solve that instance. So this example shows that among all of the hard distributions generated by Yau's minimax principle, some distributions are easy when there are a lot of input samples. So this is the main question we addressed in this paper. We show that there exist distributions that are hard even if there are infinitely many samples. So more formally, we defined this problem called correlated samples problem, which is essentially a multi-input sample version of randomized query complexity. So here we are given k input samples drawn independently from distribution D, but conditioned on that they have the same output value. So essentially, the k input samples come from this distribution half d0 to the k plus half d1 to the k. And since all of the input samples give the same output value, the task is just to figure out whether the output value is 0 or 1, and by making queries. And the core of f is defined by the number of queries you need. And so basically, we showed that there exists a distribution D where solving the correlated samples problem requires theta R of f queries. So this means that there are hard distributions where even if you have multiple input samples, it's still hard. It's even if you have multiple samples, you would rather just query the first sample. more samples wouldn't help you much, wouldn't help you more than a constant factor. So the existence of such distributions is quite useful for certain applications, especially for proving composition theorems. So composition theorem asks this question. So you have two Boolean functions, f and g, and you can compose them. And you want to know the complexity of the composed function. So the open question asks about whether the randomized query complexity of the composed function is lower bounded by the product of the randomized query complexity of the two individual functions. And this is false, shown to be false by a very recent work. In this work, we show a version of this composition theorem very easily using our main result. Yes, it's just extending previous proofs on block sensitivity to fractional block sensitivity using our hard distribution from the correlated samples problem. And in fact, in concurrent to our work, Ben David and Blaise showed a tight randomized composition theorem. And in their proof, they actually need to use a hard distribution for the inner function g, and that distribution can also that distribution can also be generated from our theorem, from our hard distribution for the correlated samples problem. And I think that's all I wanted to say. Thanks.
Thank you. Are there any questions? I maybe have a question about this composition theorem. So had you have something that depends on the block sensitivity, but in its full generality, you say that by this result of Ben David and Blaise, it will it's not true for all functions. But is there something more in between, something that would generalize your results, but still?
Right. In fact, in their paper, in Ben David and Blaise paper, they showed a tight composition theorem for partial functions, generalizing our results about
that's the one that you just mentioned.
Right.
Mm-hmm. I was also wondering, this idea of having multiple samples, do you think that this could be useful in other applications as well, or in other settings?
So I guess probably in, for example, communication complexity or other settings. I'm not I don't have a very good idea, but I think it's kind of interesting to generalize Gauss minimax principle in various settings. And I think allowing more input samples could be one way to do this.
All right, thank you. Are there any further questions? If not, then thank you very much, Lunja.
Thanks.
Further questions can always be asked in the Slack. So let's move on to the next paper on optimal set disjointness.
Hello.
Hello, Tri. Yes, I can hear you, and I see
Okay.
your screen.
Great.
Please go ahead.
Okay. So our paper is about optimal set disjointness and set intersection data structures. This is joint work with Virginia Vasilevska-Williams. And what I'm going to try to do briefly in the few minutes that I have is essentially define the problem and explain what kind of progress this paper manages to obtain. So let me start by defining what the problem is. So the set disjointness problem, the input is a family of sets, let's call it F, and we want to pre-process this family of sets to be able to answer set disjointness queries. Where set disjointness queries, so given two sets, for example, given set S1 and S4 in this example here, we can see that both sets contain the white element, so the two sets are not disjoint. So the query should answer that the sets are not disjoint. In the second example, the input is 2 and 3, so we look at the two sets S2 and S3, and we can see that the two sets are disjoint. So the query should answer that the two sets are indeed disjoint. The efficiency of the data structures and algorithms that we're going to consider are going to be measured in terms of capital N, which is the sum of the sizes of the sets. So in this example here, capital N is going to be 9, because there are a total of 9 elements in all of the sets. Now, there's some naive algorithms which either use linear preprocessing time and linear query time, or quadratic preprocessing time and constant query time. And if we denote the, I hope you can see my mouse, but if you denote the preprocessing time by n to the p power and the query time by n to the q power, then we get that the two extreme, almost trivial solutions over here give us, here it's p equals 1, q equals 1, and here p equals 2 and q equals 0. So the sum is 2. And indeed, you can actually trade this off and get what we call the heavy light algorithm, an algorithm with this curve for all the possible trade-offs between p and q that lie on this line of p plus q equals 2. So we know that this is an upper bound for the problem. And there's also a conditional lower bound based on the three-sum hypothesis that, together with Eli Parat and Seth Petty, proved in SOTA 2016, that shows that any trade-off curve has to be above the line of p plus 2q equals 2. And there's this gap over here. And the question that we address in this paper is this gap, what is a real story? How to close this gap? So what we show is, the first thing we do is we design a new algorithm whose runtime is here on this weird-looking curve over here, reduced fast matrix multiplication. Over here, as you can see in the top left here, it's optimal. Over here, there's some gap. But if we take this further, if we, for example, assume that omega equals 2, omega being the exponent in the time for fast matrix multiplication of two square matrices, then we get this kind of curve. So everything's optimal over here until the point of q equals 1/3 and p equals 4/3. And over here, we still have some weird gap here on the bottom right that we still don't know how to explain. Okay, so then the next step is really to add, we close the gap for the top left, but we still have the gap for the bottom right. We also introduce, how do we close this gap? So we introduce a new hypothesis that's related to the time it takes to detect triangles in unbalanced tripartite graphs. So by unbalanced, I mean that we have a tripartite graph, and then between the different sets, there might be different number of edges between different parts of the graph. And we can show that for this problem, we design algorithms using the known techniques, and we hypothesize that these algorithms are optimal. Again, assuming omega equals 2, we managed to show to completely close the gap and get a nice bound that covers the entire spectrum. So supposedly, assuming omega equals 2, our algorithm is optimal. In addition, there's also the set intersection version, where the goal is not just to for the query not just to establish whether the two sets are disjoint or not, but enumerate all the elements in the intersection. And in this case, the same heavy light algorithm works for the set intersection version as well. We still have this line of p plus q equals 2. And we have a matching lower bound, also from the three-sum hypothesis. But the matching lower bound only works until q equals 2/3, between 0 and 2/3, and p between 4/3 and 2. And there's this weird gap here in the bottom right as well. And by doing the same thing for triangle detection, extending the same ideas to triangle enumeration, we're able to close this gap also by introducing the unbalanced triangle enumeration hypothesis, which has to do with unbalanced tripartite graphs and enumerating the triangles in those graphs. Okay, so just to summarize, so we designed some new algorithms for set disjointness, unbalanced triangle detection, and unbalanced triangle enumeration. we show that if we believe the unbalanced triangle detection hypothesis and assume that omega equals 2, then our new set-disjointness algorithm is optimal. We also close a gap for using the unbalanced triangle enumeration hypothesis, close a gap for set intersection. And as an open problem, so a lot of the lower bounds that are based on the three-sum hypothesis follow through the set-disjointness data structure. So a natural question to ask is whether one can actually design faster algorithms for a lot of these problems using fast matrix multiplication, because in a lot of these problems, there's still some kind of gap that it's not clear that fast matrix multiplication can help do things faster. That's it. Thank you.
All right. Thank you very much. I saw that there were two questions on the Slack, and maybe I'll handle them in the order that they were asked, and ask the people to ask them themselves. So Philip asked the first question. Philip, do you want to ask it?
Sure. So, I mean, my question is, in a sense, the obvious question. So you introduced two new hypotheses. So what is the truth? Do you believe that it will turn out that there is no faster algorithm, or that perhaps even for some setting you can improve upon unbalanced triangle detection or enumeration?
So my answer is going to be very annoying. I'm going to challenge your question. Okay, I don't think belief is part of the issue here. I think the point is that the point of conditional lower bounds and these hypotheses is to say that it doesn't seem likely that unless we come up with new techniques that we're going to be able to beat those bounds. Okay, so I don't know what to believe. I do believe that you need new techniques to beat those bounds. I don't know what to believe about the true complexity of the problem. So I hope that's a fair answer, but right. So yes, I do.
I was kind of expecting that answer, right? I mean,
okay.
But I mean, the curve is kind of weird as it is right now. I mean, there's this weird, like, spike in there somewhere. Like, do you think this should be there, or? So
which spike? Let me go back to the slides.
I mean, for set-disjointness, like there in your slides.
This here?
Right? Yeah, exactly.
This here. This is the reason we have this break off is because multiplying two rectangular matrices, the behavior of the runtime really depends on what do you have more, rows or columns. So in this point where they meet is where we are talking about squared matrices. Somewhere in the problem there are squared matrices, right? But over here, in one side of the row there are more rows, on the other side there are more columns, and that really affects the runtime. This is also known for rectangular matrix multiplication. If you want to try to use various techniques, this just happens. It just pops up. It's very clear once you play around with this why this happens. I don't know if it's necessary or not, but it's very clear why it happens. I hope that answered the question.
Thanks.
Great, thank you. Then I saw a question by Aaron. Aaron, if you're here.
Yeah, I'm here.
Hi, Aaron.
Hey, very nice talk.
Thank you.
I wanted to ask about space complexity. So if you, it's possible I'm missing something obvious here, but it feels like if you have many like medium-sized sets, then just storing all the heavy pairs could actually involve more than order n space. And so I was curious what's known if you insist on no more than like order n space, whether you can still get these kinds of curves.
So there are some lower bounds. This is by Payman Afshani and Jesper Nielsen, I think, from ICALP a few years ago. I think it was an ICALP, where they show that if you assume the pointer machine model and you're looking at the sign intersection version, then because you can somehow construct the queries in a way that require you to look at a lot of different cell memories, and that gives some kind of lower bound, space lower bound. For set-disjointness, unfortunately, not much is known. There are some conjectures out there and some proofs based on these conjectures, but it's not clear. I mean, that's wide open, I would say. Yeah, I definitely agree that it's not clear that you need so much space. I definitely agree.
Okay, cool. Thanks.
Thank you. Are there any further questions? Maybe I have one quick question.
Mhm.
So you mentioned that it might be interesting to use fast matrix multiplication for other problems that have been proved threesome hard. So if I remember correctly, there are many problems in computational geometry that are proved threesome hard, or like that have a geometric flavor. Do you think that there are problems in that direction that could, for which this question could be interesting, or do you have any specific problems in mind?
Well, I would urge anyone who's interested in looking at this, looking at a paper, at our SOTA paper from 2016, and looking at Amira Booth and Virginia Vassalsky-Williams paper from, I believe it was Fox 2014, with looking at the problems that go through threesome. Also going back to Mikhail Petrosky's paper from SOC 2010. There's a bunch of papers over there, and references, papers that refer to these papers might be good options. Any particular candidates, I don't think I'd have time to really define a reasonable problem here in the given time. Regarding the geometry versions are really about offline problems, not data structure problems. So we're talking about the Gadget and Overmars paper from 95, where they introduced a bunch of these, for the first people to introduce a bunch of these lower bounds. These are really about looking at the whole problem offline and solving it offline. And I don't think you're going to be able to break the threesome conjecture because those reductions are tight, up to maybe some polylog factors. But I do think that if you're looking at these kind of data structure versions that go through set-disjointness, from threesomes to set-disjointness to these other problems, there is a gap there. And it seems due to this, I would guess that at least some of those problems you can improve using fast matrix multiplication.
Thanks. Yeah, that sounds really interesting.
I think so.
Yeah, me too. All right. So
I have one question. If
oh yeah,
okay.
Please.
Sorry. Yeah. So it's actually kind of a dumb question. I thought I figured it out myself, but seems like I have not. So just the simple set disjointness problem. So there's a solution, right, where you can, so for all the sets that have size at most square root n, you then store all the pairs of the intersection, and then anything else, the query time is going to be at most square root n. So doesn't that give you linear space and square root n query time? So how does that, because that doesn't seem to fit on this heavy light curve.
Well, the point is right here. I don't know if you can see my mouse. Can you see my mouse?
Yeah, I can see your mouse.
That's this point right here. That's a point that you're talking about. That's exactly this heavy light algorithm is exactly this algorithm. Just instead of using square root of n, I'm using some n to the alpha for some parameter alpha.
Okay, but
between 0 and 1. And the issue, so the curve here isn't addressing space at all. It's just addressing pre-processing time versus query time.
Oh, okay. Yeah. Okay, that makes sense.
Okay.
Yeah.
So for larger pre-processing time, which means that you're looking at larger sets, you're expecting to have less sets, so less memory. But for less pre-processing time, you expect the sets to be, actually it's the other way around. If the sets are pretty large, then you expect the space usage to be pretty small. If the threshold's large, the number of sets to be pretty small, so you need less space. If the threshold is small, then you expect the number of sets, the sizes of the sets to be, the threshold to be smaller, then the number of sets is going to be larger, so you're going to need more space, at least using this solution. Okay.
All right. Thank you very much.
Thank you.
I think now is a good time to move any further discussions to the Slack and move to the next paper about dynamic range mode. I think Yin Zan is standing by to briefly talk about this.
Yes. Hi. So
Hi. Please go ahead.
So in my joint works with Bryce Sandlot, we studied dynamic range mode. So this problem asks us to maintain a sequence A, and we need to support insertion an element and delete an element from the array A. And each query asks for the most frequent element of a given interval of the array. So if the sequence has a size bounded by n, it is known for a while that we can achieve both update and query in O tilde n to the 2/3 time. So there are some log factors. Recently, Anzan et al. Improved the query and update time to all into 2/3, so removing all the log factors. On the lower bound side, if we assume the online matrix vector multiplication conjecture, then there can be no algorithm that achieve n to the 0.5 minus epsilon time for both update and query for any positive epsilon. So essentially, the upper bound now is n to 2/3, but the lower bound is essentially n to the one half. So there's a huge gap between upper bound and lower bound. So we aim to, we want to close this gap. In this paper, we make this gap smaller. There's a recent related work by Vasilevska, Williams, and Xu on batch range mode. So the difference between batch range mode and dynamic range mode is that in batch range mode, the array is fixed and all queries are given in advance. Previously, the best known algorithm for batch range mode runs in n to the 1.5 time, but they improved it to n to the 1.49. So their approach is first reduce batch range mode to a special case of mean plus product, and then use fast matrix multiplication to solve this mean plus product instance faster than brute force. So we try to adapt their idea to a dynamic setting. Due to the dynamic nature of this dynamic range mode problem, naively just computing a mean plus product and store the answer somewhere cannot work. So we come up with a new problem called the mean plus query problem, which can be seen as a data structure version of mean plus product. So using this new problem and combined with their approach plus some technicality, we get n to the 0.656 time algorithm for dynamic range mode. So previously it was n to 2/3, so we get improvement in the exponent. Questions?
Thank you. Are there any questions? Maybe I can ask a question. So you're using this min plus product this query version, and if I remember your talk correctly, it was because there's also some very specific going on with how this is used, and in this min that it has some specific demands that for which you can make it work. Is this something that is that you see in other problems as well? Is this could this be used in other settings, do you think?
I see. So first, if the matrices are arbitrary, then we cannot beat brute force because this query version of mean plus product is harder than mean plus product, and mean plus product itself does not have a subcubic time algorithm if the matrices are arbitrary. So this special version of matrices are the same for the batch range mode problem. And there are many other problems, many other static problems that use special mean plus product. For instance, there are this RNA folding problem and like maximum subarray problem. Both are studied. One of them is studied by Breman et al. 2014, and the other is studied by the Williams and Xu 2020 paper. So we expect this, we can adapt some of these to the dynamic setting, but we haven't investigated this idea fully. So it's an interesting direction to looking for.
Yeah, that sounds like a great direction for some future work. Are there further questions? If not, then thank you very much.
Thank you.
Then we move to the final paper in this session on longest common substring. And I think Carl is here.
Okay, I'm here. Do you hear me?
Yes, I can hear you. I don't see your screen
do you
yet.
see my screen and mouse?
It's now
okay.
I can see. Yeah, now it moved there. Yes, thank you. Please go ahead.
So I will present a short introduction to our paper about dynamic longest common substring in polylogarithmic. Let me first state what is the problem. So basically here we are thinking on substrings, so consecutive fragments of string, so slices of string. So we have two strings. The LCS problem, longest common substring problem, is that we are given two strings and we want to find the longest string that occurs as a substring both in S and T. Yes, so we don't want to confuse it here with another famous problem that shares the abbreviation. Yes, so thinking about longest common substring here. And this problem was solved around in 70s by Weiner, who presented a famous paper on suffix trees. So this has linear time solution. So what we considered was a dynamic variant of this problem. So we asked the following question, like we are allowed to perform letter substitutions in either S or T. So in any of the strings, we can update the letter to another one. And the goal is to efficiently maintain what is the LCS after such update. Yes, so whenever we make an update, the string changes slightly. And the question is, what is the new LCS? So of course, with such dynamic problems, the question is, can we do something better than recomputing from scratch? So the answer was yes, but yeah, I will show it in a second. So we also considered another variant, which is called partially dynamic LCS, where we are allowed to perform letter substitution only in one of the strings. Yes, so there is one static string and one dynamic string. So this is the partially dynamic, and fully dynamic is that we are allowed to make letter substitution in any of the strings. So as I said earlier, it was already known that something better than linear update time is possible. In 2019 paper, there was for partially dynamic variant with only one dynamic string. There was a paper that showed that it's possible to get root of n times some polylog factors for update time with n polylog n space. So what we did in our paper is we reduced this time to log square n with the same space. And also we observed that if we're allowed to use a little bit more space and 1 plus epsilon, then it's possible to construct even faster algorithm with log n update time. And also on the lower bound side, if we are allowed to use n polylog n space, then the query time and like update time and the query time should be at least log n over log n. This is for partially dynamic LCS. For fully dynamic, the previous result was n to 2/3 times some polylogs. So what we did is we achieved polylogarithmic update time. So the exponent in the logarithm is not 2 anymore. It's larger, but still constant. And on the lower bound side, we showed the same update time, that any algorithm should take at least log n over log update time. But even if we allowed, even if you are allowed to use poly of n space, yes, so even to n to power of c. So this is for fully dynamic LCS problem. So the main idea for partially dynamic LCS is to basically maintain block decomposition of the dynamic string. So each block should appear in the second string that is static. This produces anchors, and this decomposition should be maximal in the sense that we cannot merge any two blocks to still have appearance in another string. Then from this we store these anchors, like the strings generated by anchors going from left to and right part from anchor in try. We solve Havis-induced ancestor queries. We store results for blocks in a max heap of candidates. So that's like sketch of idea. I think it's quite difficult to describe the paper in it. For full dynamic, it gets a little bit harder because the block decomposition, we cannot maintain block decomposition, because if any character in the second string changes, then the block decomposition of this can be completely different. Yes, so we have to maintain hierarchical block decomposition of two dynamic strings. So this is the idea of this locally consistent parsing that was known earlier. And you know, the other parts are basically just trying to use this idea to obtain the dynamic solution. Yes, so other parts are relevant to the LCS problem directly. So this 2D range search tree and so on. So do you have any questions?
Thank you very much. Yes, Tobias nicely posted the question that is also on the Slack. Let me read it, because I don't think Andrea...
I see the question, and yes,
good.
you can read it and I will try to answer.
So the question is, what about the use of a point structure and the role of it in the reduced problem when you use this HIA query, and how to calculate the time complexity of insertion and deletion? Can you provide some more details on them?
Yes, this is quite difficult question, but I will try to answer. So the idea of fully dynamic is to perform several reductions to simplify problem and to create several auxiliary data structures. So on the last stage in our reduction plan, basically we maintain some structure for each pair of heavy paths. So basically these tries that we create from the parsing that generated anchors, the anchors generate some pairs of strings that are kept in compacted tries. And we split these tries into heavy paths by using some dynamic heavy light decomposition. And for each pair of heavy paths, we have this additional structure. And the idea why we need this point structure is that we need to somehow get the answer. What is the answer for this particular pair of heavy paths? So we have several possible candidates on these heavy paths. These are connected somewhere in the heavy paths, and the location on the heavy paths is x and y coordinate of the points. So we need to find out what is the best the best pair of points that guarantees to have the largest length, because we want to maximize the length of the LCS. And basically, this is what we solve by using this this dynamic point structure. To answer the question, how fast or how slow is it? Basically, we use 2D range search tree. Yes, so one insertion comes with log square n cost, and yes, sometimes we need to perform more operations when the structure of heavy paths changes, but this all amortizes to polylogarithmic cost. So I hope that answers the query.
Thank you. I was wondering if maybe there is another question from further participants. If not, then you can always ask it on the Slack. Thanks very much, Carl, for your presentation and answers, and thanks to everybody in this session. Thank you very much.
Thanks.